All right, let's dig in. Today we're talking about soil, and we're going to trace its incredible story. A journey that, believe it or not, starts with solid rock and ends up as the ground right under our feet. I mean, you walk on it every single day, right? But have you ever really stopped to think about what it is, where it actually comes from, or how it was even made? Yep, you heard that right. The very soil that holds up our houses and grows the food we eat, it all starts its life as tough, solid rock. So how in the world does that happen? Well, let's get into it. Okay, so to really get soil, you gotta start at the beginning with its parent material. And that whole story kicks off with this massive geological engine, the rock cycle. You can basically think of it as the planet's own giant recycling program. Seriously, rocks don't really get destroyed, they just transform. You've got magma cooling down to become igneous rock, then that rock gets broken down into sedimentary rock, which then gets cooked and squeezed into metamorphic rock, and eventually it can all melt right back into magma again. It's this amazing endless loop, and it's what gives us all the raw material for soil. So first up, igneous rocks. These guys are literally born from fire. They're what you get when molten magma cools down and solidifies. Sometimes it happens deep underground, giving us stuff like granite. And sometimes it's from a volcano erupting on the surface, making something like basalt. These are the OG rocks, the originals. Then you've got sedimentary rocks. Now these are built from pieces. Imagine other rocks getting broken down into tiny bits. We call them sediments, right? And over millions of years, those bits get piled up, squished together, and basically cemented into a new rock. That's how you get things like sandstone or limestone. And finally, metamorphic rock. This is what happens when you take an igneous or sedimentary rock and put it under some insane heat and pressure. Not enough to melt it, mind you, but just enough to completely change it. Its whole chemistry and texture get a makeover. So, shale turns into slate, granite becomes gneiss, a total transformation. And here you can see the whole thing in action. It's beautiful, really. Magma cools into igneous, weathering breaks it down into sediment, that sediment gets compacted into sedimentary rock, heat and freshen turn that into metamorphic rock, and then extreme heat can melt it all back to magma. Now, I want you to focus on that second step, weathering. That one, right there, that's the absolute key to making soil. So, how exactly does a giant boulder turn into tiny grains of sand? Well, that process is called weathering, and it basically comes in two main flavors. Okay, on one hand, you have mechanical weathering. This is pretty much brute force. Think of ice expanding in a crack and splitting a rock, or wind just blasting it with sand. It's all about physically breaking big rocks into little rocks. But then you've got chemical weathering. And this is more like alchemy. It's wild. Something as simple as slightly acidic rain can actually dissolve minerals in the rock, changing its chemistry and creating totally new stuff, like clay. All right, so once weathering has worked its magic, we've got the basic ingredients for soil. But how do those little rock fragments actually become the soil we see all around us? Well, sometimes the soil just forms right where it is, staying put on top of its parent rock. We call that residual soil. It's kind of like homegrown soil. And if you were to dig a pit, you'd see a cool pattern. Fine stuff at the top, and it gets chunkier and more like rock the deeper you go, until, bam, you hit solid bedrock. But honestly, most of the time, those weathered bits and pieces go on a journey. You've got glaciers, rivers, wind, even just gravity. They all act like a giant transportation system, carrying particles miles and miles away from where they started. When they finally settle down in a new place, we call that transported soil. And this is what covers most of the planet's surface. Now, out of all the different soil particles we've talked about, there's one that is just on another level. It's totally unique, and understanding it is a real game changer. So let's dive into the secrets of clay. See, here's the thing. Clay isn't just a tiny piece of rock, not like sand or silt. Those are just miniature versions of their parent rock. No, clay is different. It's the product of that chemical weathering we talked about. Its particles are crazy small, shaped like little flakes, and their whole structure is fundamentally different. To really get clay, you have to think small, like atomic level small. The first basic building block is something called a silica tetrahedron. Just picture a tiny little pyramid. You've got a silicon atom right in the middle and 4 oxygen atoms at the corners. The second piece of the puzzle is the alumina octahedron. Now, these two shapes, the tetrahedron and the octahedron, they link together to form these huge flat sheets.
It's almost like atomic chainmail. And how those sheets get stacked on top of each other is what determines what kind of clay you have and what it can do.
And this is where the magic happens. Because of tiny little imperfections in that atomic structure, the clay sheets end up with a net negative electrical charge. It might sound like a tiny detail, but trust me, it has massive consequences.
So that negative charge acts like a tiny magnet for water. The clay particles literally pull water molecules in and hold on tight, right in between those atomic sheets. And that is why clay soils swell up when they get wet and then shrink and crack when they dry out. All those unique things about clay, how it gets sticky, how you can mold it, it all comes down to this invisible electrical charge.
Okay, so we've gone on this incredible journey, right? From a giant mountain of solid rock, through weathering and being moved around, all the way down to the atomic structure of a tiny clay particle. But why does any of this actually matter? So why does this whole epic journey from mountain to mud even matter to us? Well, it turns out that understanding a soil's origin story is the absolute key to predicting how it's going to behave. And that has huge implications for pretty much everything we build.
Think about it. Is the ground you're building on a residual soil that came from granite? Or was it dropped there by a glacier thousands of years ago? Is it sandy, or is it one of those tricky clays that's going to swell and shrink? Answering these questions is what allows engineers to design foundations that don't sink, dams that don't break, and hillsides that don't slide. I mean, literally, every major construction project depends on being able to read this story in the soil.
So, the ground beneath us, it isn't just dirt. It's a slow-motion story of creation and change, written over millions of years. The real question is, are we listening to what it's trying to tell us?